Is it known notion or not? What is compact operators? No, okay. So definition. Let X, Y are Banach spaces and we have bounded operator. So I remind you that this is bounded operator. It is compact. If for any M bounded set in X, the image of this set AM is pre-compact in Y. So by this notation I mean all AX for any X belong to M.
A is operator.
A is operator, yes. This is a notation for bounded operators. And it is a compact if makes from any it's make from any bounded set a precompact set. It's better to remind you some topics on our lecture on precompact sets, and if space is of infinite dimension, then the bounded set can not be precompact. For example, unit ball is not precompact in norm space with infinite dimension. And any bounded operator makes from the bounded set. So precompact, the compact operators, it makes the bounded set smaller. It's in some naive sense.
For the confirmation, compact sets are complete. Compact sets are complete. For completeness.
It's compact operator. It is not compact.
They are complete.
It's compressed space. So it's make space looks like finite dimensional. Looks like it's approximately. So it's compressed space. It's infinite dimensional space or compressed bounded sets. So some examples. For example, if you remind the linear algebra when we study only finite dimensional spaces, we have orthogonal matrices, unitary matrices, symmetric matrices, yeah, but we have no compact. Why?
Because they can take any value.
All operators are compact in finite dimensional space. So examples. Dimension X, dimension Y is finite, plus some norm. We need some norm because we want to obtain the norm operator, but in any norm in finite dimensional space, your operator, linear operator will be bounded. So all operators are compact. Because what bounded operator make with bounded set? It preserves boundedness, yes? It preserves boundedness. In finite dimensional space, precompact sets are just bounded sets. Compact sets is bounded and closed in finite dimensional space. In finite dimensional space, not in infinite dimensional space. In infinite dimensional spaces, we need some additional assumptions on our set. It's we prove it in LP small and in space of continuous functions.
To make it
When additional assumption when the bounded set become compact set, precompact set. But what now make some extension of this picture. Operator acts from X to Y. And we see that for this definition, important the property of this set in space Y. So if only Y is finite dimensional and A is bounded, then operator is compact. It's compact. Why? It's easy to understand. Operator is bounded. We make a bounded set M, obtain bounded set AM, because operator is bounded, but this set lies in finite dimensional space Y. Bounded set in finite dimensional space is precompact. But more, let's by this image or range of operator. It's synonymous. Image of operator or range of operator is just all elements from space Y for which we can find X, that Y is AX.
Here xy are the initial and final points.
What?
Bxy.
Bxy, it is bounded operators.
They are initial and final points.
It is from space X to space Y. It is initial and this is the goal. So it is just not free, it's image. I remind you the definition of range of operator. And the rank of operator is dimensional of image. It's dimensional of image. And operator has finite rank if the rank of operator is finite. And third example, A is bounded from X to Y, and rank of operator is finite. Rank of operator is finite. Then again, from these two items, you can conclude that A is compact. Is compact. Because operator makes from X to the image. And if image is finite, then finite dimensional, then and operator is bounded. It is important. You can construct an example of operator which has rank 1 but unbounded. There is examples of such operator. It is possible that operator has rank 1 but without this property, but unbounded. Infinite dimensional space, yeah, of course, because in infinite dimensional space, infinite dimensional space we have this. But for some aspects, this is, definition is not convenient. We must work with any bounded set. But sometimes it is useful to change bounded, all bounded set on a special bounded space. I prove one statement, and you see what we can do. Okay, so theorem. Let X, Y, R Banach spaces. Then A is bounded from X to Y. Then A is compact if is precompact set in Y. This is a unit ball in space X. This is unit ball with center 0 and radius 1. So if you see, we needn't to check any bounded set. It's sufficient to check what happens with the unit ball. For one direction proof is evident, yes, because this is by definition. If A is compact, then image of any bounded set is precompact. This is a particular case of bounded set. So we immediately obtain this. Yes?
How is this thing is pre-compact setting by?
What?
How it is pre-compact setting by? As you said something here, the image of.
So we should prove the inverse. So, right. If AM is precompact, for any M, then ABX01 is precompact to. Yes? So, the inverse. Let M some bounded set. Some bounded set. Then it lies in some ball, yes? It means it's bounded, then exists some positive number R, that for any x from M, the norm of x less than R. It is the same that M lies in unit ball, or not unit ball, but with ball of radius R. Yeah? It is the same. It's by definition. So, and what we know? We know that A is following S A is precompact. Who remember Hausdorff criteria?
For every epsilon exists NX.
Yes, the criteria of precompactness. It is totally bounded. Yes, so it is existence of finite network.
Yeah.
Yeah. So then, for any positive epsilon exists Yn, Y2, Ym finite network for image for A, B, X, 0, 1. And then idea is simple. Idea is to construct the some finite network for the image of arbitrary bounded M. What idea? What you can do with? You see that this set lies in ball with radius R. What first step to do with this network? I state idea Ry, Ry2, Rym is epsilon multiplied on R network for AM. Check this. So for any x from M, AX minus R Yi, then we choose this index I. You can write it as this difference. What you can say about norm of this element? Norm of this element. Less of 1. And but these elements, this sequence, constructs the epsilon network. So what we can say, for any x, we can find there exists such index I that this is less than epsilon. Yes? But then you multiply this less than epsilon. Yes? Because these elements are network, epsilon network. Then it is less than R multiplied by epsilon. But epsilon is arbitrary. R is the property of set M. It is bounded, it lies in some ball. It radius of this ball.
But what does means with R by 1? Means it is
You multiply it. It's
R by
multiplication. It's our space Y is a linear space. You can multiply elements on the number. It is this element. This is from Y. And this is you multiply these elements on number R. And it is a network, not epsilon, but R multiplied on epsilon. But epsilon is arbitrary number. We can do it for any epsilon. For example, for epsilon divided on R. So for the follow, it is more convenient because it's sufficient to check this property only for one set, which is very good unit ball. Okay, so the properties of compact operators. So let's define by this set, by these numbers, Cxy. Cxy compact operators. From X, all compact operators from X to Y. So I think it is clear why I choose this letter, C. Compact. B bounded, C compact. So properties of compact operators. Three simple and one not simple. Theorem 1. Let again take Banach spaces. A, B are compact operators from X to Y. Then its linear combination is compact operator 2. So compact operators forms linear subspace in space of all bounded operators. Proof. Let's prove it. It's easy. Let Y1, Y2, Ym is epsilon network for image of a unit ball by acting of operator A. Let Z1, Z2, Zn epsilon network for what operator? B. B. Yes. For operator B. Let's say, write this here. it is operator and this is unit ball. So idea that alpha yi plus beta zg I from 1 to n, g from 1 to n is not epsilon, but epsilon multiplied on some constant network. Is network. Just calculate this epsilon network for alpha a plus beta b acting on unit ball. Let's check, but here some question. I don't remember epsilon. I just calculated what is the size of this network. So for any x from this unit ball, what we can write? Alpha a plus beta b x minus alpha yi plus beta zg. And later we choose these indexes I and g later. By triangle inequality, I take this with this and this term with this term and use the triangle inequality. So it is less than absolute value of alpha ax minus yi plus beta not a but bx minus g. What you can say about any norms here? What you can say about this? Ax is the range, is image of unit ball, no? And for any x, what you can say? This was epsilon network for this set. So there exists I such that this norm less than epsilon. Yes? By definition of network. And here we can say there exists g such that this less than epsilon. And sum we obtain the sum of absolute values alpha plus beta multiplied on epsilon. So we obtain not epsilon, but epsilon multiplied on some constant network. So just this is the answer for this question. That's all. So linear combination of compact operators is compact operator. Second theorem. Again, let x and y are Banach spaces. Not. For theorem 2, I need a lot of Banach spaces. A is compact from x to y. B is bounded from y to, for example, z. And C is bounded from w to x. I need a lot of spaces and just this rule because I want to construct the composition of operators in a correct way. All with space, we need all this space only for construction of composition in right order. So then from this, what the order? First A, then B, yes? A acts from x to y, B acts from y to z. So BA is compact operator from x to z. And this first C from W to X, then you can act by A from X to Y. So AC is compact operator from W to Y. shortly, composition of bounded and compact operator is compact operator. Doesn't matter in what order. Doesn't matter, in what order. Hmm? The composition of compact operator and bounded is compact operator. It doesn't matter, it's right multiplication or left multiplication. In algebraic terms, we know that all bounded operators forms the algebra. It is grouped by sum, it's semi-grouped by multiplication in one space. We x from x to x. And it have property of linear spaces, so it is algebra. Compact operators is sub-algebra, of course. We proved it in the first theorem. It is a linear subspace, so it is sub-algebra. But if multiplication from one side preserves the, if we take an element from the ring, and multiplicate it on from the, for example, from the right on the element of semi-ring, and we obtain the element from the semi-ring. From the algebraic terms, what it means. Ring, it is a group on one action, and the semi-group for multiplication.
You said that
So the term ideal. You take a ring and multiply the, if you have a ring and you have a semi-ring, for example, and you multiply the elements of the whole ring on elements of semi-ring and obtain again the element of semi-ring. So it is right or left ideal. So compact operators is two-side ideal. Later I formulated for ideal, it is we need to take one space. But this is, again, main property of compact operator. The composition of compact operator with bounded operator is compact operator. It's compact operator. So let's prove it. It is not difficult thing.
So BA here belongs to CXZ.
B, it's different letters. It's B is here operator, and this is bounded operator from Y to Z.
So will AB also will lie to C to Z?
It is
Will the order matter here?
this is the order of spaces need us construct this order of first operator A from X to Y, second B from Y to Z.
If we inverse the order now, it's
But here I can't change the order, can't, because space is different. But if you work in one space, in one space, so consider situation that A is compact from X, B is bounded in X, then AB, BA is compact operator in X. When one space, it is more, you can write it more shortly, you take one operator, one bounded. It doesn't matter in what order you multiplicate them. So in this situation, we can name that compact operator is two-side ideal. It's two-side ideal. Question?
why you said that the bounded operator is semi-group in the
It is semi-group on multiplication,
why?
because we have no inverse operators. For arbitrary operator, the inverse operator doesn't exist in multiplication, but it is group in sum. The inverse operator in sum is minus A. A plus minus A is zero operator. So it is group. Moreover, it is commutative group. So proof of this theorem. B, okay, so what you can say about this set? A is compact. This is unit ball. So by the property of compact operator, it is pre-compact set. In Y. So for any epsilon positive exists Y1, Y2, Ym epsilon network. Find it. Epsilon network for what? For A, B, X, 0, 1, for the image of the unit ball. Then I claim that this is norm B multiplicated epsilon network for BA 0, 1. So we change the size of this network, but epsilon is arbitrary. Why it is so? Why it is so? I check it here. Let X from the unit ball in space X, capital, then and this is in space, what, where? In space Z, yes? Here B, in space Z, yes? This element lies in Y, this element lies in Y, but then we X by operator B, and we obtain elements from space Z, yes? So this norm is in Z. But by multiplication inequality, we can write this inequality, this estimation, yes? And we know that for this norm, there exists I such that this is less than epsilon. So we obtain that it is less than for this. So we only change the size of our network. So it forms norm B multiplied on epsilon network. Because epsilon is arbitrary, it is sufficient. So it is clear, yes? This. And the second property is more easy. It's more easy because this will prove, yes? First, what you can say about this? C acts from W to X. So we take here unit ball in W. What you can say about this set? C is bounded operator. So what you can say about this set? It is bounded set. Bounded set. Where? From W in X. And A is compact from X to Y. A is compact from X to Y, so we immediately obtain that A, C is pre-compact set in Y, by definition. The image of any bounded set is pre-compact set. And theorem 3. Let X, Y are Banach spaces. We have the sequence of operators, and for any n, an is a compact operator from X to Y. And an tends to operator A by norm. By norm. So what is conclusion about operator A? Is compact. The limit of compact operators is a compact operator. If limit is by norm. If you remember, we have strong operator convergence and weak operator convergence. In this sense, the property of compactness doesn't preserve. Only norm. Only norm. So, a conclusion, A is compact operator from X to Y. So proof. Take some epsilon, positive. What we know? We know that there exists number n natural which depends on epsilon, such for n less or equal for this n capital, the norm of n minus a less than epsilon. So it's just a definition of the convergence. Then take some n greater. And x by this operator on unit ball in space X. What we can say? It is precompact. It's precompact. In Y, so for the same epsilon, there exists Y2, Ym epsilon network. Let's check what happens for these elements and for image of unit ball, but not by operator an, but for operator A, of the limit operator. So take x from X such that it is from unit ball. And later we choose some good index Y. So we can write it as and subtract the same element, and then use the triangle inequality. Yes, triangle inequality. This term we estimate as A minus AN multiplied on norm X. This less than 1 because it's from unit ball. Yes? And this is less than epsilon, so it is less than an epsilon. And here, what you can say here, for any x you can find the proper index I, yes? Because they form a network. So we can say that here exists such I that this is less than epsilon. So in sum we obtain the estimation 2 epsilon. You can formulate theorem 1, 2, 3 in one sentence in short way if you act in one space. So it is summarizing of theorem 1, 2, 3. When you act in one space, so we can consider two-sided ideal. So multiplication from the left, multiplication to the right preserves the compactness in the ring of all bounded operators, in the ring of all bounded operators. So you compare that. In theorem 2, we have a lot of different spaces in order to construct in correct way the composition of operators. But if we have one space, we need to do it. So in one space, it's more easy. So algebraic terms are known or not? Ideal, two-sided ideal. No?
Maybe not know what is an ideal. Or
Ideal just the property of compact operators. You have a ring, you have subring. And you multiplicate, for example, any elements from the whole ring, left multiplication to elements of subring. And you obtain an element of this subring. So it is named the left ideal. If it is the same to the right, you have right ideal. So for example, take the space of all matrix N. Matrix N on N. Is it a ring? It is a group by sum, and it is semi-group by multiplication, yes? So it is a ring. You have two operations.
So you have two operations, it's a ring.
And group on one operation and semi-group to another operation.
Okay,
That is ring. That is a ring. If it is additional linear space, then ring with the linear space is algebra. Not a science, but construction. So all matrices and all operators, all bounded operators, for example, this space is algebra. And consider, again, come back to the matrices. Consider the matrix with a zero line.
zero.
Zero line. You have matrices A from Mn yes, this is matrices of n size, quadratic matrices. And then consider matrices, for example, B, which looks like B11, B1n, and Gth line is 0. What you can say about this matrix? What you can say about this matrix? What? Just the same, with the same number. By the rule of multiplication of matrix, the Gth line of this matrix is 0, 2. So all these matrices with the 0 lines is a left ideal. You multiply matrix from the left, and you obtain the matrix with the 0 line, with the same property. It is left ideal. If you take a matrix with the 0 column, it's right ideal. It's right ideal. But for finite, for matrix, there are no non-trivial two-sided ideals. But for operators, we have compact operators. Because in finite dimensional spaces, all operators are compact. So one-sided ideal you can construct, yes? But two-sided. So, and one more property of compact operators. Do you remember our theme on different convergence? Weak convergence, star weak convergence. It is not easy theme, but it is important. Why? What do you think? You have a sequence which weakly converges, and you have bounded operator. What bounded operator make with weakly convergences sequences? Remark. Let xn weakly converge n in x. A is bounded operator from x to y. X and y Banach spaces. For simplicity. Spaces. bounded operator preserves weak convergences. Why? By definition. By definition of convergence, weak convergences, and definition of adjoint operator. So let's check it. For any f from y star, yes? This sequence lies in y. So we need to check this, we need to take the functionals from a dual space for y. So f a x n, and this is just a question, yes? We need to check it. By definition of adjoint operator, how you can write it? This is. You must change the order and take the Banach adjoint operator, yes? So it is equal to A prime F, X on N, and this is G from X star, yes? Because Banach adjoint operator acts from Y star to X star. A acts from X to Y, and A prime acts from Y star to X star. So it is, but we have weak convergences. We have weak convergences. So what you can say about this? It is to this, yes? By definition of weak convergences. For any functional, just for functional g, which equals A prime f. And then you again change the order and you obtain this. So it is indeed true, yes? So bounded operator preserves the weak convergence. And spoiler, what make compact operator with weak convergence? Try to guess. Any compact operator is bounded operator, so it preserves. But it is compact operator. It make it norm, yes. It make it norm, it's make stronger. So theorem 4, yeah? On property of compact operators. Theorem 4. We have Banach spaces. We have weak convergence sequence, and we have compact operator. And we have compact operator. Then the new sequence converge in norm. Converge in norm. So we prove it by contradictions. Let's suppose that we have no norm convergence. Let's suppose that we have no norm convergence. Then what? If we write the contradiction to this to convergence, so we can say that there exists positive number C, and there exist subsequences of indexes which tend to this infinity, such that this, no? But what you can say about this? This is subsequence, yes? we know that x and k converge to x. We know it because it is subsequence. And we know that A is a bounded operator, not only compact, it is a bounded operator. So it preserves weak convergences. But set x and k is weak convergence, so it is weak bounded. From this, and as corollary from Banach-Stengel theorem, it is bounded. Banach-Stengel's theorem bounded. A is compact operator. So this set A, X, and K is precompact. I need to use third order indexes. So exist nkg tends to infinity such that x, nkg tends to the sum element y and y, yes? A compact operator, so it is precompact set, so we can find the subsequence which is converged. And additional, we know that x nkg. And additionally, we know that nkg tends, to this element, but weak convergence, because we have weak convergence of this, of double indexes. So we have weak convergence for the subsequence with triple indexes. Question, is y is the same element as x? If y is the same element, y, it is correct, but why? Yes, we have this stronger convergence. Yes, we have norm convergence. So we have weak convergence. Additionally, we have that A, X, and KG weakly convergence to Y, because from the norm convergence, we obtain the weak convergence. And if Y is not AX, second corollary from the Banach theorem, Hahn-Banach theorem. If you have two different elements, you can find the functional which differs these elements. And exist functional from this space such that Fy not Fax. And this contradicts to what? This then contradicts that we have weakly convergence to Ax and weakly convergence to Y. So we have weakly convergence to this and weakly convergence to this. And if we take functional f, we obtain that they are not converged. So it's one contradiction. So this contradicts to these two convergences. Yes. So we obtain then that are the same. And the final contradiction will be what? We have A, X, and KG tends to the AX, and we have this. And this is subsequence of this subsequence. For whole subsequence, we have estipation below, and here we have a convergence. So this is a contradiction. This is final contradiction. This is final contradiction. So our assumption was wrong. But there is examples of operators which makes from weak convergence strong convergence, but this operator is not compact. It is not a criteria of compactness operator. It is only one side implication. If we have weak convergence, have compact operators makes changes to the strong convergence. But if we have operator which makes any weakly converging sequence to the strong converging sequence, it may be not a compact operator. But in reflexive spaces, it is a criteria. If operator acts in reflexive space, it is compact if and only if it changes any arbitrary weakly convergent sequence to the strong convergent sequence. Do we have a home problem? In space L1 small, the weak convergence coincide with the norm convergence. The special property of space L1 small. The weak convergence in this space coincide with the norm convergence. Take identity operator and act by this operator identity on any weak convergence sequence. But this sequence converges in norm. So we can say that identical operator change the weak convergence to the strong convergence. But identical operator in infinite dimensional space is not compact. Okay. So why compact operators are important? These operators arises in many applications in mathematical physics. For example, they arises as inverse operator to differential operators. For example, as when you try to obtain the solution of some differential equation, you can write it with the integration operator. And very often the integration operator is a compact operator. And so we prove some theorems on integral operators. So we consider operator AF of type AB so it is just a definition of an integration operator, integral operator. And theorem 1 of this integral operator, if kernel of this operator is continuous function in two variables on the square, then operator A is compact in what space? In this. In compact in space of continuous functions. I want to emphasize that this is not a criteria. It is a sufficient condition. But it is very close to the necessary condition. I don't prove the criteria, but we prove the simple situation for sufficient condition. And criteria looks like that it is kxy function, kxy cannot be continuous on finite numbers of continuous curves on the square AB on AB, which are the graphics of continuous functions. So let's prove. So what we need to check? We need to check that the image of the unit ball is a precompact set. Yes? So we take awful construction, yes? But this means the unit ball in space of continuous functions. Or maybe Maybe I write in such way. I think you know it is the same. It is the same, but in different way, right? Do you remember the criteria of precompactness and space of continuous function? Arcellas-Colli theorem. Boundless and equicontinuity, yes? Equicontinuous. So first, boundless. We know that this operator is compact. Not compact. We know that this operator is bounded. And we have a problem, we task when we find the norm of this operator. But we can repeat it again. So let's repeat these estimations. This less than the norm, less than 1. And so we obtain that it is less than maximum for x and integration by the second variable, dt. For any f with unit from unit ball. So we obtain that the set is bounded, yes? And second, equicontinuity. Let's take epsilon, arbitrary epsilon. And we know that our function is continuous on the square. Square is a compact. What property we need for continuous function on compact?
Its image is compact.
Hmm?
Its image is compact.
No, it's yes, but we not need another property. Any continuous function on compact is uniformly continued. Uniformly continued. So exists delta positive such for any if the distance between arguments less than delta, then less than epsilon. I just remind the definition of uniform continuity. Yes? Let's take x1 and x2 with this property. So take x1 minus x2, then take it. Then by definition of our operator, make one integral as difference of function k and put the absolute values inside. So we obtain the estimation what you can say about each factor inside the integral. What you can say about this difference. By this property, t is the same argument, but x1 minus x2 less than delta. Then we immediately obtain that this is less than 1. And this is from the unit ball. So it's less than the norm, which is less or equal to 1. So we obtain that it is less than epsilon multiplied on the length of the interval. But epsilon is arbitrary. So we obtain equicontinuity. Equicontinuity. It's a criteria of precompactness set of in space of continuous function. The set must be bounded and must be equicontinuous. So this is just as uniformly continuous, but for any function from the set.
Okay.
For any function from out of the set, there exists epsilon. For any epsilon, there exists delta. That if the difference between arguments less than delta, for any function from set M, f of x 1 minus f of x2 less than epsilon. We have this about lesson lecture 3 or 4.
Sorry, question. Formula, is it called equicontinuous or uniformly equicontinuous?
I need both too.
On a compact, it's the same thing. On a compact.
No. Uniformly continuous, it's uniform by arguments.
No, I mean,
They lies in anywhere. But equicontinuity, it is uniform estimation for any function. It's for arguments and for the functions.
I understand. I mean, I think there is a concept of equicontinuity and uniform equicontinuity. just like with continuous functions, you have continuous and uniformly continuous, and with equicontinuous, you can have just equicontinuous and uniformly equicontinuous.
It's for one function they coincide on a compact, yes, for one function, and for finite set of functions. But if you have a set, the set which contains infinite functions. We have examples. For example, this set in this space is not equicontinuous. It's not equicontinuous. Because in the neighbor of point 1, the distance between arguments is not small. If you consider all functions simultaneously. All functions simultaneously. Because for large n, it is increases from almost 0 to 1 on very small interval. So it is so equicontinuity is uniformness for functions and for arguments. Uniformly continuous is just for the arguments. So and another space more useful, more convenient for us, more useful for us, because in physics Hilbert space more important than Banach space. So we can consider integral operator in space L2. In space L2, and another assumption is from L2 on two variables. Then it is operator is compact in this space. If kernel is integrable in square by two variables, so it is in L2 of two variables, then our operator is compact operator. It is too sufficient condition, but it is far from the necessary condition. It's just a one class of so-called Hilbert-Schmidt operator. Hilbert-Schmidt operator, class of operators. Later, when we discuss the Hilbert-Schmidt theorem, we discuss another ideals. The compact operators is the largest closed ideal, but we can consider not closed ideals. It's some subclasses of compact operators. For example, this is some subclass among all compact operators. It's so-called Hilbert-Schmidt operator. If it is an integral operator with such kernel. And then I describe class of Hilbert-Schmidt operators in terms of so-called singular numbers. Singular numbers, but we discuss this only when we consider obtain the Hilbert-Schmidt theorem. The idea of this theorem, the idea of the proof, the idea construct operators an which tends to A in norm and an are compact in L2. Then by theorem, the third theorem of the property of compact operators, the limit operator will be compact. The limit operator will be compact. And how construct these operators an? Easy. Why? Let system phi I is orthonormal basis in L2. It is orthonormal basis. So then system is orthonormal basis in this space. We divide variables. You take arbitrary basis in one-dimensional space, and by multiplication, by division of variables, you construct the basis in two-variable spaces. And then construct operator an. Because it is basis, and this function belongs to this space, so you can represent it as a sum of basis elements, yes? So function kxt can be represented as sum for ig, ceg, pceg, yes? A Fourier series. We have a representation of function as sum of basis elements. So consider function knxt sum eg from 1 to n, both indexes. So summation by square. And then construct operator an. What you can say about operator an? What you can say about each operator an? The hint, the sum for chi n is finite. It is operator of finite rank. It is operator of finite rank. Why? Let's write it in details. I put the formula for function psi, and then write it as sum for e to 1 n this is looks like we take integral by variable t and we take sum by index g. So it is some number which depends on I. So the range of operator is finite linear combination of these functions. So what you can say about the rank of operator an? Any function from the image of operator is finite linear combination of functions phi with indexes I from 1 to n. So rank of operator is most n. And we have a task for estimations of norm of this operator. We know that the norm of operator an less or equal of the norm of this function in this space of two variables. So we have bounded operator with finite rank. We have a bounded operator of finite rank. So we obtain that these operators are bounded from bounded. Compact operator in L2AB. And what we need is to check what happens with this. But what you can say about operator an minus af? It is again integral operator. It is integral operator, yes? But with this kernel, with the difference. And we know again that then the norm of this operator by the same rule can be estimated as the norm of these functions in L2 of two variables. But this Kn is the approximation by basis representation of function k. So it tends to the 0 as n tends to infinity. So A is the limit operator of compact operators. So A is compact. Okay? So we finished with compact operators. Can begin a new theme. Invertible operators. So inverse operators. I remind the general situation without node linearity only on transforms of two sets, for example. Yeah? We have set X, we have set Y. Well, let's X, Y linear spaces. A is linear operator, just linear operator. In infinite dimensional situation, we need to distinguish two inverse operators, the right inverse operator and left inverse operator. Left inverse operator identity in what space? x. Right inverse operator is identity in y. If it exists, if it maybe not exist. And moreover, left inverse operator is not unique and maybe not linear. Hmm? Unique that you can construct two different left inverse operators. But let's discuss what property of operator corresponds to the existence of for one of the inverse operator. If exists left operator, inverse left operator, then it is easy to understand that operator must be injective, or the kernel of operator A is 0. So from this property, we obtain that the kernel, if exists, so operator is injective, and if exists right operator, then the image of operator A must be y. It is last, so he must have full image, full range. So if you have left inverse and right inverse operator, you immediately obtain that your operator A is B action. Moreover, if exists left inverse operator and right inverse operator, they are the same operators. They are the same operators. So if exists A and this operator, then A is B action and the operators coincide. B action is immediately obtained from these properties, yes? The existence of left inverse operators implies the injection, and the existence of right inverse operator implies the surjection. So both inverse operators implies B action. And why left and right inverse operators coincide? Construct this composition. We know that the composition of operators, it's defined by point, yes, is associative. Associative. So associative, the result of composition do not depend on brackets. You can take brackets in such a way, then you obtain that it is identity, and then you obtain that it is a right inverse operator by these brackets. And you can take brackets in such a way. Then you obtain identity here. Then you obtain left inverse operator. Okay? So let's consider some examples.
So they both exist, are they unique?
If exist left and right, they are unique. They are unique. Because it is B action, must be. So in this situation, we don't write the indexes. If exist two-sided inverse. They're the same, so we do not write the index in this situation. Example. Let's consider operator of left shift and L2 small. Can you, is it have the inverse operator?
In this case, isn't the adjunct operator the same as the inverse
so-
operator? Maybe it's the left shift.
If inverse operator exists, it must be B-action.
Okay.
But you consider the first basis vector in kernel, lies in kernel.
Yes.
The vector 1, 0, 0, 0 by operator AL get to the zero sequence. So we have a kernel. We have a kernel, but the range of this operator is whole space. It is a surreaction, but it is not a B-action because it is not an action. It is not an action. So if it is, so it have no. If we have a kernel, we have no left inverse operator, but we have you can construct right operator.
The right shift.
The right shift. You see that if you say construct this, you shift all sequence to the right, then come back to the left. So it is identity. So the right shift is the right inverse to the left shift. But the inverse composition is not identity. This is a projection on the orthogonal complement to the first basis element.
Yes, yes.
Because we go to the left and you come back to the right, so the first coordinate will be 0. But let's construct to the right shift, the left shift, different left inverses. The problem, you have right shift operator. Can you construct the left inverse to this operator?
Isn't it like right square?
The left shift.
Left shift and others.
This is
It is left shift, yeah?
The inverse operator of the left shift multiplied by the right shift, right?
Hmm?
What's written in there is the inverse operator of the left shift
Yes.
multiplied by the right shift.
Yeah.
Didn't you just say that the inverse operator of left shift is just right shift?
The inverse of operator to the left shift. It's not inverse. It is only right inverse. It is only right inverse.
Yes.
So you, by this property, we can say that I R is just this combination. Yes, it is right inverse to the left shift. Yes. But you can construct different right inverse operators. Different. For example, consider such operator. The right shift puts on the first coordinate 0, but I consider another operator which put on the first coordinate any number. Any number. It is not linear operator, first. If A is not 0, it is not linear operator. But all these operators are inverse to the left shift. But one side inverse. But one side inverse. And let's prove one simple theorem. But if exists inverse operator inverse operator, not one side inverse, but inverse operator. So A is biaxial. Then this operator is linear. You see that it is possible that one-sided inverse may be not linear, and it is not unique. But if you have a biaxial, it is of course unique, because we have one-to-one correspondence between elements x from x capital and elements y from y capital. And in this situation, the inverse operator is linear. So, proof, we must check how it acts on this linear combination. Yes, inverse operator x from y to x. But we have the property of surjection, of biaxial, so we can write y1 is this act of operator A on some unique element x1, yes? And y2 is the result of acting of operator A on the unique element x2. And A is linear. A is linear, so you can write as but again, because x, we have a biaxial between x capital and y capital, you can write x1 as so we immediately obtain the linearity. If exists linear operator, inverse operator, then the inverse operator is linear.